In this video, we're going to be going through Chapter 6.1, which is Verifying Identities. Now, this is kind of the one of the major topics of all of Trig. And if you've never seen this or worked through something like this before, it could really be a challenge because it's kind of a different way of thinking about math than probably what you've seen in the past. So, to start, what is an identity? An identity is an equation that is true for all numbers for which both sides are equal. So what we mean by this, well, let's look at an equation. Let's say we have this equation, 3 plus x equals 2x minus 9. So if we solve this, we're going to get 12 is equal to x. Now, what this is saying is the only value for this equation that is going to make the left side equal the right side is when x is equal to 12. Now this is slightly different than an identity because in an identity we can actually input any value for x and it's going to make the left side equal the right side. So an identity is kind of a more broad type of equation. Now we've already seen a few types of identities in this class. We've seen what are called the reciprocal identities, and what we have here is, well, one identity, sine theta. We know that sine is the reciprocal of cosecant. So sine theta equals 1 over cosecant theta is a reciprocal identity. And again, what we mean is any angle we put in for theta, the left side will equal the right side. And then there are 5 other reciprocal identities. And what we have is cosine theta equals 1 over secant theta, tangent theta equals 1 over cotangent theta, and so on. So these are the reciprocal identities that we've already seen. The other set of identities we have already seen are called the quotient identities. And these are tangent theta equals sine theta over cosine theta. And similarly, cotangent theta is equal to cosine theta over sine theta. So these identities, the reciprocal identities and the quotient identities, we have already seen. Now, one thing I want to mention is, as you're watching these videos, it may be a good idea to, on a separate piece of paper, all of the identities that we see, to kind of make a bank of those so that you can refer to them as we're working. You will need to have these memorized. So anything I highlight, I guess, as an identity, you're going to have to commit that to memory. So this is what we've seen so far in the class. Let's move forward to some new identities. So next let's talk about what are called the Pythagorean identities, and the Pythagorean identities are going to come or get derived from a right triangle. So if we have angle theta here, x, y, and let's say the hypotenuse r has a length of 1. Now if we take sine of that angle theta, well, sine is just going to be y over r. Because r is equal to 1, this is just equal to y. And then if we look at cosine theta, this is going to be x over r, and since r is equal to 1, this is just equal to x. Now, sine theta equal to y, let's square both sides here. So we're going to get sine squared theta equals y squared. Similarly, let's take cosine theta, square that, and take x and square it. We're going to get cosine squared theta equals x squared. And now what we see is, well, this y squared and x squared, if I take x squared plus y squared in our original triangle, that's just going to be r squared, which is equal to 1. Okay, and what we see is that we can substitute sine squared for y squared, and we can substitute cosine squared for x squared. So what this leads to is, I'll write it like this, cosine squared theta plus sine squared theta is equal to 1. So there is the Pythagorean identity, kind of the most basic version of the Pythagorean identity. And again, so what this means is any angle we pick, if I take cosine squared of that angle, and I add that to sine squared of that angle, it will always equal 1. Now there are a couple different versions of the Pythagorean identities. So this is the first one, to to know. And then there's two other versions. So starting with our original version, if we divide through each term by cosine squared theta, well, cosine squared divided by cosine squared, that's equal to 1. Sine squared over cosine squared, well, that's just tangent squared. And that's going to equal 1 over cosine squared. Well, 1 over cosine is secant, so this is secant squared theta. So this is a second version of the Pythagorean identity. And then let's derive a third version. Well, if we go back to the original Pythagorean identity, now let's divide through by sine squared. Sine squared. And what we're going to end up with is cosine over sine, that's cotangent. So cotangent squared theta plus 1 is equal to 1 over sine. Well, that's cosecant, so we get cosecant squared theta. So this is a third version of the Pythagorean identity. So we have three different versions of the Pythagorean identity that we need to know. Looking at this example, if cosine theta equals -5/13 and theta is between pi and 3 pi over 2, find tangent theta. Well, this restriction just means that we are in quadrant 3, okay, and tangent is positive in quadrant 3, so this is going to be a positive value here. So we're going to look at two different ways we can do this. The first way is what we've seen previously. If we draw a right triangle in quadrant 3, theta, well, cosine is just opposite, or rather adjacent over hypotenuse. So the adjacent side to this angle is going to be -5. The hypotenuse is 13. And then what we can do is we can use the Pythagorean Theorem to solve for this value y. So y squared equals 13 squared. We get 25 plus y squared equals 169. And solving for y, we're going to get a y value of 12. So plus or minus 12 when we take the square root of both sides. We know that this has to be -12 because y is going to be negative in the third quadrant. And then once we have that, we can just find tangent of theta. Tangent is opposite over adjacent. This is going to be -12 over -5. And then the negatives cancel. We get 12 over 5. So that is one way we could go about solving this problem. Let's look at a second way. And the second way is going to use one of these Pythagorean identities. So if we want to find tangent theta, well, let's use the Pythagorean identity that has tangent in it. Okay, so tangent squared plus 1 is equal to secant squared theta. Well, we know that secant is just the reciprocal of cosine. So if cosine is -5/13, that means secant is going to be -13 over 5. What we're going to do is we're going to take this value, plug it in right here for secant. So we're going to have tangent squared theta plus 1 equals -13 over 5 squared. And then let's just solve for tangent. So tangent squared theta plus 1 is equal to 169 over 25. Then we need to subtract 1 from both sides. Well, 1 is the same thing as 25 over 25. So we'll say tangent squared theta equals 169 over 25 minus 25 over 25. We get tangent squared theta equals 144 over 25. And then let's take the square root of both sides. This leads to tangent theta equal to plus or minus 12 over 5. Now, because we're in quadrant 3, tangent is positive in quadrant 3. So the final, we're only going to use the positive value here. So ultimately, we're going to end up with tangent theta is equal to 12 over 5 as our solution. Okay, and that squares with what we had over here in this the other method that we used. Now, looking at both of these side by side, we can clearly see that The first method is a little quicker. However, we can use the identity in this way to find the value of tangent. And then another set of identities that we will use are called the even and odd identities. So if we recall, a function is odd if it's symmetrical about the origin, whereas an even function has symmetry about the y-axis. So looking at the functions, the 6 trig functions, some of them are going to be symmetric about the origin, some of them will be symmetric about the y-axis. And similarly, the test for a function being odd, well, we need to show that f of negative x is equal to negative f of x. For a function to be even, f of x must equal f of negative x. So, which functions are odd, which ones are even? Well, let's talk about the even ones first because there's fewer of them. So if we look at the graph of cosine, a cosine graph, remember, starts positive. This is pi over here, 1, negative 1. So cosine graph is going to go something like this. And if we go in the negative direction, we'll have this. Now, and this is f of x equals cosine x. Now, despite this drawing, the graph of cosine is symmetrical about the y-axis. So what we would say is that cosine is even. And because cosine is an even function, what this means is cosine of x is equal to cosine of negative x. And similarly, the reciprocal function of cosine, which is secant, well, if we were to draw the secant graph, it's going to come off the peaks and valleys of the cosine graph. So f of x here in red is equal to secant of x. And what we see is that is also symmetrical about the y-axis. So secant, we would say secant of x is equal to secant of negative x. So those are the even functions. Now, the odd functions we can find in the same way. If we look at the graphs of sine, cosecant, tangent, and cotangent, we will find that those are symmetrical about the origin. So I'm not going to graph those here. You can do that on your own. But we see that each of these remaining trig functions are odd. So what this means in practice is that sine of negative theta is equal to negative sine theta. That's just the definition of what it means for a function to be odd. The reciprocal function is odd, or the reciprocal of sine is odd. Cosecant. And then tangent and cotangent are similarly odd. I made a mistake here on cosecant. Let's back up a sec. Cosecant needs to be written like this. Okay, and then moving on, cotangent of negative theta is equal to negative cotangent of theta. So there we go. And for the even and odd functions, you want to have these committed to memory. One way we use these trig identities is to simplify expressions that have trig functions in them. So what do we mean by simplifying a trig expression? A trig expression, we say, is simplified if we get down to a single term, and that's if possible. It's not always going to be possible to simplify a trig expression to a single term, but if we can do it, we would need to. A trig expression will be simplified if there's no fractions. So again, we're going to try and remove any fractions, and then we're going to try to simplify down to a single trig function. So sometimes a trig expression will have many different trig functions within it. We want to combine and condense into a single trig function, and again, where this is possible. So let's look at a couple examples of this. So the expression we have is cotangent of x plus tangent of x plus cosecant x secant x. And what we need to notice here is, well, back to what we're trying to do, we want to get down to a single term, no fractions, and one trig function. Now what we notice is that, well, we have three different terms here, so definitely not a single term. And then we have four different trig functions. We have cotangent, tangent, cosecant, and secant. So let's try to get down to one term and get down to a single function if possible. Now, strategy that I'm going to apply here is I'm going to convert everything into sine and cosine. Now, this strategy may not always work for us. Because I've done this problem before, I know that it does work. But as we're working through these types of problems, sometimes you're going to try a strategy and it'll prove to be beneficial, sometimes it won't. And so there may be times where you travel down a road and it's a dead end and you need to regroup. So let's try this strategy. Let's convert to sine and cosine. And the reason that this is a good strategy is because all of the trig functions can be written in terms of sine and cosine. So cotangent, we could write that as cosine x over sine of x. Tangent, we can write as sine x over cosine x. And then plus cosecant is 1 over sine, and secant is 1 over cosine. Okay, so we have gotten this down into two different trig functions. And what I'm going to do here is, well, this fraction I can write as 1 over sine x cosine x. And then these two fractions here, I would like to add these together, and to do so I need a common denominator. So the common denominator between these two fractions is sine x cosine x. So this first fraction I need to multiply by cosine x over cosine x. Here I need to multiply by sine x over sine x. And doing so, we're going to get cosine squared times cosine squared, which is, cosine x times cosine x is cosine squared x over cosine x sine x, plus the second fraction I get sine squared x over cosine x sine x. And now what we notice is that all of these denominators are the exact same. So we can write this as a single fraction. We're going to write cosine squared x plus sine squared x plus 1 all over cosine x sine x. Now we have a single fraction, and what we notice here is that cosine squared x plus sine squared x, that's just the Pythagorean identity. And cosine squared x plus sine squared x is equal to 1. So what we can do is we have 1 plus 1 in the numerator. That's going to be 2 over cosine x sine x. So we're pretty well simplified here. We do have a fraction and we have two trig functions, but we do have a single term. There's one last step we can take. If we say 2 times 1 over cosine x times 1 over sine x, well, cosine x, we can write that as secant, and 1 over sine x, we can write that as cosecant. So we could ultimately write this as 2 secant x cosecant x. So that would be the simplified version of this expression. Now there's a lot of steps here, and if you're not familiar with the trig identities that we're using, this is going to be a challenge for you. So the best thing you can do to start seeing how this works is to really memorize and be totally comfortable with all of the trig identities that we've seen so far. Let's look at a second example. This one's not in the notes, but I wanted to do one that's maybe a little simpler. So 1 over 1 plus tangent squared x. Well, what we can notice is that tangent squared x plus 1 is equal to secant squared x. That's one of the Pythagorean identities. So what we can do is we can take this 1 plus tangent squared x and substitute secant squared x. So we can rewrite this as 1 over secant squared x. And then secant squared x is the reciprocal of cosine. In other words, 1 over secant squared x is equal to cosine squared x, and that would be the simplification there. And then back to the notes, we'll do that last simplification example. What we have is tangent x over secant x plus 1 plus tangent x over secant x minus 1. So the strategy that I'm going to employ here is to combine these fractions using a least common denominator. So use LCD to combine fractions. And this one is quite a few steps, so I'm going to try to write a little bit smaller here. So we want to combine these fractions by using the least common denominator, and the least common denominator here is going to be secant x plus 1 times secant x minus 1. So on the left fraction, I'm going to multiply by secant x minus 1 over secant x minus 1. And then on the secant x plus 1 over secant x plus 1. And doing so, in the numerators, I'm not going to multiply this out just yet. Secant x minus 1 times tangent x plus secant x plus 1 times tangent x. And then we have a common denominator. The common denominator is going to be secant x plus 1, secant x minus 1. And then in the denominator, I'm going to actually multiply that out. So for the sake of space, multiplying that out, we're going to get secant squared x plus secant x minus secant x minus 1, and then those two terms cancel out. So what we end up with in the denominator is secant squared x minus 1. Okay, and what we have is, well, we know that tangent squared x plus 1 is equal to secant squared x. If we subtract 1 from both sides of this equation, we're going to get tangent squared x equals secant squared x minus 1. So what we have is secant squared x minus 1. We can replace that with tangent x. So I'm going to do that in the denominator, and then in the numerator, let's factor out the tangent x, because we have a tangent x in each term here. So tangent x, and then what we get is, right, like this, secant x minus 1 plus secant x plus 1. And then in the denominator we have tangent squared x. So this tangent x that we factored out, that's going to cancel or factor out with one of the tangent x's in the denominator. And then in the numerator, if I just add these two expressions together, well, the 1 and the negative 1 are going to cancel. We're going to get 2 secant x over tangent x. So we're almost there. At this point, I'm going to rewrite everything in terms of sine and cosine. So 2 times 1 over cosine x all over sine over cosine x. Now when we have a complex fraction like this, in other words a fraction divided by a fraction, we can rewrite this as 2 in the numerator, 2 over cosine x divided by sine x over cosine x. Well, when we divide fractions, it's the same as multiplying by the reciprocal. So cosine x over sine x. And what we'll see is that these cosines cancel. Okay, you don't need to necessarily go through this step if you see right away that the cosine cancels. And then we are left with 2 over sine x. And if sine x is in the denominator, this is the same thing as cosecant x. So ultimately we're going to have 2 cosecant x. So many steps there. And again, if we are familiar and comfortable using the basic trig identities, this shouldn't be too bad. but if these trig identities are brand new for you, getting to this point to be able to work with a problem like this, it's really going to take some practice.